All right, problem 10 deals with Gauss's law of electrostatics, and it says that E is an electric field. The flux integral of E over some surface S is called the electric flux through the surface S. Okay, so it's a bit of a disclaimer before pressing on. For those of you that have taken some electricity and magnetism, now you know that electricity doesn't really flow in the same way as a fluid across a surface, but nonetheless, the math that describes electricity and fluid flow have a lot of similarities. And so this idea of electricity flowing across a surface, while maybe not technically correct, it can often lead to some good intuition for how these systems behave. Okay, and this term flux here and electricity flowing, right? All these terms are still nonetheless applied oftentimes to electricity. Okay, and so now what does Gauss's law say? It says that the net charge Q enclosed by a closed surface S is proportional to the electric flux through the surface S. So more specifically, it says that the net charge Q is equal to this constant epsilon naught times the electric flux through the surface. Okay, and this constant epsilon naught is known as the permittivity of free space, and here is an approximate value of epsilon naught in SI units. All right, so part A says suppose that the electric field here is this radial field that satisfies the inverse square law, right? It's the same field we looked at in the last video, and our surface S is, well, the same surface as in the last video. It's the sphere of radius A centered at the origin. So our job is to use Gauss's law to find the net charge Q enclosed by the sphere. And again, the sphere is oriented so normal vectors point outward. All right, so we've really done all the calculations in the last video. The flux integral we found was 4 pi k, so that implies that the net charge Q enclosed by this sphere is 4 pi k times epsilon naught. Okay, now as a side note here, if you just take into consideration that our vector field E here, the electric field is radial, okay, at every point along the sphere, it's parallel to this outward pointing normal vector. And furthermore, the dot product of E and N, well, that's just magnitude E times magnitude N times the cosine of the angle between them. Well, since they're parallel, theta is 0, so the cosine is 1. And N is a unit vector, so it has magnitude 1. And the magnitude of our electric field along the sphere of radius A is what? Well, if I take the magnitude of this thing, the position vector R, right, that just has magnitude A, so I get A over A cubed is 1 over A squared, and that's going to get multiplied by K. So this dot product is K over A squared, and in particular, this dot product is constant on the sphere. Okay, so we can also compute this flux integral as just saying, well, this thing is constant, so just pull it out front. So it's going to be that constant K over A squared with our epsilon naught in there from Gauss's law times this integral over the sphere of just ds. And that's just the surface area of the sphere, which is 4 pi a squared. And you see the a squareds drop out, and you wind up with 4 pi k times epsilon naught. So if you take a course in electricity and magnetism, this is likely how you will proceed in computing net charge. Okay, you'll take advantage of things like symmetry in the fact that this dot product here is just constant over your surface, so it winds up really boiling down to just a surface area calculation. Okay, well, in any event, let's press on now to B. Okay, so here you genuinely need calculus. You can't get away with this kind of symmetry, constant dot product sort of trick. So here it says the electric field E is yi plus xj plus zk, and S is the boundary of the solid region E enclosed by the paraboloid z is equal to 1 minus x squared minus y squared, and the plane z is equal to 0. Then it says, use Gauss's law to find the net charge Q throughout the solid E, assuming the boundary is oriented so that normal vectors point outward. All right, so I'm going to make a little space here. Okay, so here is the paraboloid. Z is 1 minus x squared minus y squared. And here is the base of our solid. Okay, that's just formed by the intersection of the paraboloid and the xy plane. So here Z is 0 along this base disk. And since this paraboloid is given in explicit form, right, Z is 1 minus x squared minus y squared, I'm going to parameterize the paraboloid with an explicit parameterization, right? So R of xy is just x, y, 1 minus x squared minus y squared. All right, so I'm going to get rid of this here, make a little more space. Here is the normal vector, tx cross ty, so that's just minus gx minus gy 1. And in this case, that's 2x, 2y, 1, so not too bad there. And so now, if I evaluate my electric field E along this paraboloid, okay, so I'm going to get yi, and so here I'm going to set for y, that's just, well, y, and that's going to go into the I component. So I'm going to get y there. Then xj, well, x is just x, and so that's going to go into the j component. And then zk, so that's going to give me the k component here is 1 minus x squared minus y squared along the paraboloid. So that's going to go in there for e, because that's what z is equal to. All right, so now one thing to note here, I didn't point this out earlier, but this normal vector, right, this thing 2x, 2y, 1, okay, it has a positive k component, right? So this thing does point outward, okay, and it is consistent then with the orientation that's been selected for normal vectors to point outward from the paraboloid. So that's all fine and good as well. So let's go ahead now and compute the surface integral of E over this paraboloid. So I'm going to do E evaluated along the paraboloid dotted with this normal vector. And so that's going to give us the following. So I take this vector here in purple, I'm dotting it with this red vector, and I'll end up getting this expression here in green. And what's the region R here that x and y vary over as we describe this paraboloid? Well, if I project the paraboloid onto the xy plane, I'm just going to get that base disk, right? Which is just the disk of radius 1 centered at the origin, right? Because if I set z to 0, I just get x squared plus y squared is 1. So that's saying that the radius here of this boundary circle is just 1. Okay, so to compute this integral over this disk, okay, makes sense to use polar coordinates there. So go ahead and use polar, and you get this expression here. And not a terribly hard integral, but I'm going to just leave the details to you. You wind up getting pi over 2 for this integral. Okay, so again, this is just the flux integral over the this top portion of the surface, right, along the paraboloid. We still need to look at the base disk. But fortunately there, something really nice happens, because on the base disk, z is 0. And so notice for the electric field, the k component then is 0. And so I just get that E evaluated along the base disk here is just going to be yi plus xj. Okay, and since we're choosing the normal vectors to point outwards, our unit normal vector along the base disk would just be minus k, right? Because it's pointing directly down and it has length 1. And since, right, our electric field has no k component, right, it lies parallel to the xy plane. If I dot that with n, that's just going to be 0 everywhere on the base disk. So in fact, this flux integral along the base disk is just 0. All right, so then putting all that together, we get that the net charge enclosed by this surface, right, which is just the boundary of this solid, right, formed by this paraboloid and this base disk, is equal to epsilon naught times the sum of these two values, pi over 2 and 0, and that just winds up being pi over 2 times epsilon naught. All right, now the last part of that question asked, okay, if normal vectors pointed inward instead of outward, so in other words, if we reverse the orientation for the surface, what would be our value? Well, you would just get the opposite of what we got here, because it would amount really to just choosing the opposite of the normal vector tx cross ty back up here. All right, so that is gonna do it. Thanks so much.